All right, today it's just a little check into making sure we know how to solve with series and parallel, and sometimes a combination of both types of circuits. It's all about utilizing Kirchhoff's and Ohm's law together. I'm going to really emphasize the role of Kirchhoff's laws, and Ohm's law is mostly just to kind of wrap things up. Because Kirchhoff is very much a how things work sort of law, and Ohm's is very much a this is just a numerical relation sort of law. So I find Kirchhoff's is better for explaining the whys. So one, it is helpful to remember Ohm's law that the voltage that you get across a component should be equal to the product of the current and the resistance. And so that's the first thing for us to remember. Not much to remember there, but if we take a gander here at Kirchhoff's laws, let's remind ourselves of that. First, Kirchhoff's current law, or what I call the junction rule, is all the current entering a junction must equal the current exiting the junction. So this is the current in equals the current out. And then there's Kirchhoff's voltage law, or the one that I call the loop law, is that the total voltage in a full loop is 0 volts. And remember that your sources add voltages and resistors subtract voltages. So you're looking for loops when you're looking for voltages, and that's what it is. And from those two, we were able to derive a relation on how resistors act in series, where the total resistance of a circuit is simply the sum of the resistances, and in parallel, where the reciprocal of the total resistance is equal to the addition of the reciprocals of the resistances. Between these relationships here, and using Ohm's law to fill things in, we'll be able to solve for any manner of circuits. So let's put it into practice here. What is the total current in this circuit here? Notice I have my 12-volt source, and then I have 3 resistors. In this case, if I'm talking about current, I'm thinking about Kirchhoff's junction rule, I'm thinking about the current law, and I'm seeing no junctions, no splits anywhere, which means the current is going to be the same in absolutely every part. So if I find one current, I found all currents. So that's my first bit. Think about that. Think about my junctions, no junctions. If I find one current, I found them all. Now, I don't have anything else. I have resistances on 3 different things. I have 1 voltage, but I don't have 2 pieces of information for any piece. So I'm going to use my resistance rule. Since this is a simple series circuit, I know that my total resistance is equal to the addition of my resistances. So there's 8 and 5 and 6. So that's a total of 19 ohms of resistance. And if my total resistance is 19 ohms, and you can always consider the source as your total value, V total is 12 volts. So I total, the total current, which is what we're solving for, should simply be V total over R total. And in which case that's 12 over 19. And I can punch it into my calculator and get a decimal value if I want, or I'll just leave it as a fraction, because why not? 12 over 19. Well, that's it, right? I look for it, look for my junctions, no junctions. I found that means any answer for current I find is the answer for all the currents. And I use my series relation for resistances to make it all work. Let's take a look at this second example. It is again another series circuit. There are no junctions, so that means that this current, this 1 amp, is the current on all the pieces. And we can ask ourselves, what is the voltage on this battery? There's multiple ways for us to approach it. And that's the nice thing you're going to find, is there's more than one way to approach this. We can approach this by thinking, oh, I can make my loop relation V total would be V1, V2, and V3. And since I know that this current applies to all 3 components, I can actually find, oh, V is I times R. 1 times 2, 2 volts. 1 times 3, 3 volts. 1 times 5, 5 volts. I have 2, 3, and 5 volts across these. And I know this minus 5, minus 3, minus 2 should equal 0 when I do my loop. That's one way of doing it. I just explained it, but honestly, That seems like a lot of work when I could just say, well, this is a simple series circuit. I can just find our total. Our total is 5 plus 3 plus 2. That's 10 ohms in total. And this I we know applies for all the terms, so this is I total. I total is 1 amp. So V is equal to I times R. That's just going to be 1 times 10. Oh, it's a 10-volt source. Easy peasy. Just like that. There's always more than one way to approach these problems, and that's what's really nice. This one looks a little bit crazier. Oh no, look, this is some pieces are in series, but also some pieces are in parallel. How are we going to approach this? Well, we use Kirchhoff's laws. One thing that I'm noticing is I don't know the voltage of my battery, and I'm not particularly aware of the voltage of any of my components here. So I'm going to say voltage is looking for loops. I want to find loops. There are two loops. There's this loop here in yellow, and then there's this loop here in green. And if I can find the voltages across any components, either in my yellow loop or my green loop, I can get this solved. Something that I like here is this current is 1.5 amps. Notice how it runs across this 3 ohm resistor and it runs across this 5 ohm resistor. So I can use Ohm's law, V is equal to I times R, to find my voltage in these two spots. Here's voltage, I'm going to call this 1, and here's voltage, I'm going to call this 2. Voltage 1 is going to be 3 times 1.5, that's 4.5. And voltage 2 is going to be 5 times 1.5, that's 7.5. Now if I look at the rest of yellow loop here, this is 2 ohms, but I don't know the current across it. If I'm clever, I might be able to use Kirchhoff's current law to find it out, but I actually don't need to, because I'm looking at my green loop. This V1 is part of green loop, this V2 is part of green loop, and this 4 ohm resistor is part of green loop. But notice how there's 0.5 amps running through this part here. So I can V times IR on this one too. V3 here is going to look like I times R. 0.5 times 4 is 2 volts. If I'm looking at just my green loop, 0 is equal to voltage from my battery, V total, and then if I follow through, it looks like it's, oh, sorry, not an equal sign there. I should subtract V2, follow along in my green loop. What comes next? Subtract V3, keep following along in my green loop, subtract V1. And since I got numbers for all of these, 0 is equal to V total minus 7.5 minus 2 minus 4.5. Let's see, 7.5 and 4.5 is 12, and 2 more is 14. So we get to say V total is equal to 14 volts. And notice how it's a bouncing back and forth. I use Kirchhoff to try to figure out what I know, and then once I see two values, I can use Ohm to get a third, and then I jump back to Kirchhoff, jump back to that loop law to see how that new information assists me. So it's always a combination of jumping back and forth between Ohm and Kirchhoff. But I always tend to lean on Kirchhoff to justify why I'm doing things and get me my answers, where Ohm is just to fill out those numbers. There are some more examples, ones like this and ones like this, where we can see some of them, like this one, we can't get with Ohm's law right off the bat. We have to use some relations that we know through Kirchhoff to end up solving these. So that's where we go. I'd recommend please make sure you try these with the teacher around. That'd be extra helpful, and practice more of these. This is where we're going to be going. Bye.